Okay, our next speaker is Dr. Wrigley, who's going to address the question of when there are enough model isomorphisms.
Thank you very much. Thank you to the organisers. Thank you for you guys choosing this talk. I would have preferred choosing that one, but there we go. And thank you also to Eugene and Shane for letting me prepare some of these slides for the MCAS program. Yes, the question is, when are there enough model isomorphisms, or based off the talk you saw earlier with Graham Manuel, it's we have an understanding that theories should be able to be represented by some groupoids of their models. And we're going to be doing a sort of topological parallel to that localic construction. And specifically, we want to sort of characterize in some suitable notion which groupoids of models contain enough information for us to recover the theory from that groupoid. Specifically, we're going to be proving that, understanding what I mean when I say that a groupoid of models represents a geometric theory if and only if we have these two constructions being satisfied: conservativity and this elimination of parameters. So that's the talk. Thank you for coming. But obviously, the goal at the end of this talk is to be able to pass what I mean by that. So in that regard, I have a colour-coded overview. So the first part, we're going to review some of the definitions we've already seen about what it means when I say that a groupoid represents a theory. So we're going to look at the topos of shoes on a topological groupoid, and we're going to review the definition of a classifying topos. I want to give a motivating example from the literature of a representing groupoid for a theory. In the third part, we'll define what we mean by elimination of parameters, and then finally give the technical statement of this unexplained jargon in the final part. So, we've already seen many examples of understanding internal categories. So this groupoid diagram is going to be a topological groupoid when it's internal to the top, and we have topologies making these topological spaces, and all of the arrows continuous maps of those topologies. But we're also going to make the distinction about when our source and target maps are open, and say in that case it is an open topological groupoid. When we have a topological groupoid, we can of course build the topos of equivariant sheaves on that groupoid. If we have a groupoid, we can consider a discrete bundle for this groupoid, so that's going to consist of something living over the set of objects and a lifting of the action by the set of arrows to the fibers. So we have isomorphisms between our fibers for each isomorphism between our objects. And when we have topologies being involved, when we have a topological groupoid, we're going to say that it's a sheaf if this bundle is a local homeomorphism for some topology on Y, and the action is a continuous action for these topologies. We take morphism of sheaves to be those morphisms of sheaves in the sense that that triangle commutes, and they have to be equivariant in the sense that square commutes. And when we take these objects and these morphisms together, we get a topos, the topos of equivariant sheaves. So that's what we mean by when we have a groupoid, we can associate a topos with it. The other aspect is when we have a theory, we're going to associate a topos with that. We've already seen earlier today what it is. It's a classifying topos. The intuition for classifying topos theory is that if toposes are really just generalized spaces, then a classifying topos is a generalized space whose points are models of our theory. So it's a topos with this property that the models of our theory in sets correspond to the points of our topos in this sense. And we can actually take models not only in sets but in any Grothendieck topos, and this actually then becomes a universal property for the classifying topos and defines their Taylor equivalence. And as mentioned, every geometric theory has a classifying topos, and every Grothendieck topos is a classifying topos for a geometric theory. So these are the two components. We've got groupoids, we can associate a topos with a groupoid, and if we've got a theory, we can associate a topos for that theory, and together we're going to say that our groupoid represents our theory if we have this equivalence between the sheaves on the topological groupoid and the classifying topos for that theory. The technical requirement for the characterization result that this topological groupoid has to be open, we're just going to shove that in. So when I say the groupoid represents T, that's understood to have this requirement that the groupoid has to be open. Let's have an example of when this happens. If we had a theory which had enough set-based models that they're conservative, that is the interpretation of, if the interpretation of any two formula are equivalent in all models, then they have to be provably equivalent in our theory. Under this condition, we can sort of intuit that our theory is recoverable from all of the models of our theory. And so we would like to take the groupoid of all models, but of course this is not a small groupoid, it's not an internal groupoid to the top, so we can't do that. Instead we have to restrict some suitably large sense. And I quite like this sentence. We've got small in a technical sense and large in a vernacular sense. What do we mean by suitably large in the vernacular sense? It's going to be this idea of an indexed model. So a structure over the signature for our theory is going to be indexed by a set, which we're going to suggestively call the set of parameters. It's going to be indexed if there's some subset of our parameters and an expansion of our structure to the signature where we've added a constant symbol for each one of the parameters in our subset, such that our model now satisfies this sequent, which expresses that every element of our model is the interpretation of some parameter. And equivalently, this is saying that we have a choice of partial surjection to the representing set of our model by some set of parameters. And when we take the groupoid of all indexed models by an infinite set of parameters, so this is a small groupoid because if there are only a small number of sub-quotients for the set. So this is a small groupoid, and we take all of these indexed models, and we're going to include all isomorphisms between these models. Then we have something paralleling the Joyard-Tierney construction that we had in the localic groupoid case, but now in the topological case, which is that if our parameters is infinite and the indexed models of our theory are conservative, then we have this equivalence between the sheaves on this groupoid of indexed models and our classifying topos, once that groupoid of indexed models is suitably topologized. And that happens actually if and only if the indexed models are conservative, which is, as I mentioned, that the two formulae are interpreted identically, then they have to be provably equivalent. So that was in Henrik Force's PhD thesis, and then a paper as well with Studi. Yes, so this is an example of a representing groupoid, but there are many different representing groupoids for any single topos. And so it would be nice to have some sort of way of checking, if you give me a groupoid, can I check whether or not it's going to represent my theory? And so the next section, we're going to start developing the language in which we're able to express this characterization of which open topological groupoids can represent our classifying topos. Some basic definitions. If I have an indexed model and a formula in the language of my signature, I'm going to denote the definable subset by this x phi in the square brackets. And that is just the set of all tuples of my model which satisfy that formula. Because I'm in an index model, I can also include parameters from my indexing. And so we can get a definable subset with parameters, which is the correct generalization. We just take all of the tuples which satisfy a formula, where that formula now includes parameters for my indexing. And we can do the same type of thing when we look at group-ordered models. So an indexing of our group-ordered models is just going to be an indexing of each model in our groupoid. And we can do the same deal where we now take subsets of the co-product, but we take these definables, or definables without parameters, which are pairs of a tuple and a model where in that model that tuple satisfies the formula. And with our indexing we can do the same construction when we take definables with some parameters in our formula. Once we have all of this machinery, we can note that, I'm doing this for a single sorted theory, but it's easily generalized. So for each n, we have our bundle over our groupoid of models, where we just take all of the n tuples in each model and project down into our model. And whenever we have a formula, we get a definable subset of this bundle, which is just the interpretation. And we can note that the action that we had on our models lives in, and this subset is stable under this action, in that if we start with something inside the subset, then its image under any of the arrows is still inside that subset. And that's because these isomorphisms are isomorphisms of the models, and so we have to preserve the interpretation of each formula. And the same happens if we start off. The point is that it doesn't happen when we start off with a definable with parameters. We start off with a definable with parameters, then it's no longer a case that this subset is stable under the lifting of our action. And that's because these isomorphisms between our models preserved a sigma structure, but they didn't preserve any of the indexings that we add. So they don't have to preserve the interpretation of the parameters. But of course, once we're in this setting, we can come up with a stable subset by just taking the closure under all of the isomorphisms in our model. This gives us an orbit, the definable with parameters. And in this particular example that I've written up here, we can see that actually this orbit of the definable with parameters is actually equal to the definable subset without parameters phi. This is the notion of elimination of parameters I stressed. So that's the main definition, that if we have a groupoid of T models and some indexing of our models by a set of parameters, then we're going to say that our groupoid eliminates these parameters if whenever we have a formula and some parameters n, then there exists a geometric formula without parameters such that the orbit of the definable with parameters is the definable without parameters. An example of where this happens is if we take the algebraic closure of the rationals and we consider their automorphism group. This eliminates parameters, and we can see that in a particular case here, where if we take an algebraic number, then because the Galois group of the Q bar acts transitively on the solutions of its minimal polynomial, we have that we eliminate parameters from this particular formula by the fact that its orbit is the set of solutions of the minimal polynomial. So this is an example of elimination of parameters in action. And that's it. These two properties are enough to have this classification of which open topological groupoids can represent our classified topos. And we have a geometric theory and some small groupoid of models for our theory, then there exist topologies on our set of objects and our set of arrows, making it an open topological groupoid that represents our classifying topos, if and only if we have these two properties. Conservativity, that if the interpretation of our form is the same, then they're provably equivalent, and that we have an indexing of our model by some set of parameters, such that that groupoid now eliminates parameters. Let's just do a sanity check that we're not doing something really stupid. And the sanity check is that all of the examples that I know, at least in the literature, of open representing topological groupoids can be recovered from this classification theorem. So in particular, the indexed models studied by Audi and Forsell are recovered by this classification theorem. The groupoid of enumerated models, which is to say that there's an indexing of our model where every element of our model is the interpretation of infinitely many parameters. That was the topological groupoid studied by Woods and Mordyke in the original topological representation paper. That groupoid also eliminates parameters, and we're also able to recover Caramello's topological Galois theory, which says that if we've got some nice properties on our theory such that it's atomic, well, if it's atomic, then we have this property that the automorphism group of a single model eliminates parameters if and only if that model is ultra-homogeneous, which is that every finite partial isomorphism of subsets of M extends to a total automorphism of our model. So we're able to recover old results. I want to add one new result which parallels the theory for localic groupoids. So there's this this observation in Mordyke that every localic groupoid is equivalent to its tau completion. What does that mean? In the localic case, you have to be careful by what you mean by points in the set of arrows. But for the topological case, it's more intuitively stated, which is that we've got a groupoid T models. We say that our groupoid is a tau complete. If there are two models in our groupoid, every T model isomorphism between these two models is instantiated in our set of arrows. And then we're able to observe that just like how the Joao-Tierney construction for the localic case tells you that an open localic groupoid is the sheaves on it is equivalent to the sheaves on its tau completion, we're able to do the same with open topological groupoids. That if our groupoid of T models eliminates parameters for some indexing, then if we add isomorphisms to that groupoid, that elimination of parameters is preserved. And so we end up with the fact that every open topological groupoid is a Morita equivalent to the sheaves on its tau completion, as we would expect from a localic case, but it's good to have an indication of that in the topological case. And I believe I finished very early. You're all very welcome. I'll take some questions. Thank you very much.
Well, we have plenty of time for questions. Steve.
Thanks for the nice talk. Condition of eliminating parameters, I wonder if it's related to the following observation. If we take the equivariant sheaves on the groupoid and then we just take the sheaves on the space of objects, that covers the equivariant sheaves, especially getting the action. The equivariant sheaves on the groupoid are a quotient of the sheaves on the space of objects.
You mean you have like so the topos of sheaves on the space of objects as an open surjection of the sheaves on the topological groupoid. Yes,
Right,
so...
and the fact that it is a surjection is a conservativity condition.
Yeah, but it's a surjection to the conservativity.
And openness, I think, is the elimination parameter.
I would like that to be the case.
If it says that it's an effective descent, then
Exactly.
you can cover the portion then as the descent.
Yeah,
So-
I haven't been able to do that, but I would like that to be the case.
Okay, good. Then we'd be on the same page, I think. Understanding of the situation.
I think I missed the definition. What is a groupoid of T models?
So we have a theory. We can take models of that theory in sets. I should have made that clear, but these are groupoids of set-based models. So just
So there should be a map from the set of objects to the set of models?
No, so what we have is we have the category of models of our theory T in sets, and the groupoids that we're considering are just small groupoids which are subcategories of this category.
How do enumerated models fit into that?
So enumerated models fit in because this is small, we can pick parameters. Like we can find a sufficiently large set which is going to index each of the models here. And the point is that, as I understand it, previously the idea was, well, if we take all of the indexed things, then we're definitely going to get a representing groupoid. And the idea here is that the existence of topologies on our space of objects and our space of arrows are giving you the indexings on here, and the fact that it's representing tells you that it eliminates parameters.
I guess I'm just confused because, for example, the boots and Mordek one is the most familiar with. There's more than one possible enumeration for each model.
Yes.
So
Yes, exactly. So these would correspond to different models in this formulation. We're taking, so when, yeah.
Oh, they would be different models. Okay.
Yeah. So you present each model as a different enumeration. These would give different models in your groupoid.
Any more questions?
Is there a reason that you're working with topologies instead of locales?
Yes, so the idea here is that there's more of a dialogue with traditional model theory when you use topological spaces. So if we, where am I going? Here. If we compare this result by Caramello that we get the automorphism group representing an atomic theory if and only if it's ultra-homogeneous. This stands in contrast with the localic representation theorem of João-Tierney and de Boek, which says that when our theory is atomic, we can take the localic automorphism group of any model of an atomic theory, and this gives us a representing group. But here, when we do topology, we have to impose model theoretic conditions. In this case, ultra-homogeneity, and in the more general topological groupoid case, this elimination of parameters is supposed to point in the correct direction of which model theoretic conditions we should be considering.
Thank you.
Well, some would take the opposite point of view.
Yes.
Going into locales frees you of all those model theoretic considerations.
Yes, but it's nice to have a dialogue with that field.
Yeah, question on that?
So, first off, absolutely fantastic talk, incredible presentation, thank you. I'm a bit curious, are there further applications of this result you expect? Are you working on anything in that?
Where I want this to go is, there's a lot of this is just retreading a lot of the steps made by João-Tierney and also more like in terms of what's happening in the localic case. And there's this very pretty result at the end of Mordek, which tells you that two localic groupoids are equivalent if there's a span of these weak equivalences of localic groupoids. And so I wanted to sort of go in the direction of that for topological groupoids. It's not the case that you can take spans, you have to take co-spans, and also the conditions not as pretty as elimination of parameters. So it needs more work, but that's the direction.
Yeah, thank you.
Okay, well, if there are no more questions, that